Now in class 12th, I am telling you about the LENZ'S law. This is one of the most important law of electromagnetism, and this tells you about the direction of the induced EMF and induced current. This law gives the direction of induced EMF in the circuit. Second, this law follows the law of conservation of energy. It follows the law of conservation of energy. Now in this one of the phenomena, when the magnet is brought near the coil or taken away from the coil, in both the cases there is change in the mechanical energy, and this change in mechanical energy appears in the form of electrical energy. So there is simply the change of mechanical energy into the electrical energy. The mechanical energy converts in electrical energy. So what we have? Mechanical energy. This changes to electrical energy. So now let us take the statement of this LENZ'S law. According to LENZ'S law, the direction of induced EMF is always such that it opposes the change that produces it. The direction of induced EMF is always such that it opposes the change that produces it. So, now let me take to this one. Suppose here we are having a magnet. This is a coil. This is galvanometer. This is the magnet. This is north and this is now south. Now this is brought near to this coil. The north pole is brought near the coil. It means that the induced EMF is such that it should oppose of the magnet coming near. So this will possible only when this front surface of the coil is the same pole as here. So this must be the north pole. The same pole will be repelled, so the work will be done at the cost of the repulsion. So here this is brought like this one, then this will be the north pole in this way. So current will be like this. Now current goes in this way, and this is now deflection. This is galvanometer. Galvanometer, and current will be in this way. Now if suppose this chain is carried away from this one, this is now coil, S, and this is now N, and then this is carried away. Then the direction of induced EMF is such that it opposes the motion of the coil of this magnet going away from this one. It means that there must be the south pole, the induced pole in this coil will be the south pole, so that work has to be done against the force of attraction. So this will give you the current in this way. This will pass. This is now galvanometer. This current goes in this way, and this is now. So in both the cases, there is the opposition, and if suppose I take this is the coil, and this now suppose I have this north and this is now south. Now south pole is brought near the coil. Then this will be the south pole. South pole. Like this. So this current will pass like this one. If the south pole is brought away from, is carried away from the coil, this is now south pole, this is north pole, and then this is carried away from here. Then this will be the north pole in this way. So the current will pass in this way. This is the current. So what you see, that when the pole or the magnet is brought near to the coil, then same kind of coil, the pole is induced in the coil, and when this is brought carried away from the coil, then the opposite kind of pole is induced in the coil. That gives you the direction of the current, and this work is always done against the magnetic force. When a magnetic pole is brought near the coil, the same kind of pole is induced. The same kind of pole is induced in the coil, giving the direction of and gives the direction of induced EMF. So this is when the pole is brought near to the coil. When this is carried away, so this is how to show you that this is suppose the coil and this is now magnet like this S and it's brought near to this one, then this will be the north pole brought near, this is our direction, and this suppose the magnet this is N and this is now S. Here we have the coil, then this will be the south pole when this is brought away from this one. So current induced EMF like this. This is for the north pole. Similarly, we have seen this south pole, then this is now coil and this is now magnet. This is S, this is N brought here, then this will be the south. And the induced EMF will be like this one, and here this is now N, this is now S carried away, then this will be the north pole in this way. So this shows you that when the magnetic pole is brought near the coil, the same kind of the pole is induced, brought near. This is carried away. This I have shown you about the north pole, which is brought near the coil, and if suppose this is the south pole and this is the north pole and this is like this one, then here will be the south pole. So direction of current will be like. So this is anti-clockwise and this is now clockwise. And if the magnetic pole is carried away from this, when a magnetic pole is carried away from the coil, a dissimilar pole is induced in the coil and gives the direction, induced EMF. Induced EMF. So dissimilar pole, it means that this, suppose a north, this is south and this is now north, and this is carried away from this. Then what will happen, that this will be the south. So the current will be like this, in this way. And when this having the S, and this is now this N and S, this is N and S, and this is now brought away from here, then this will be the north pole. So current will be like this one. So this is what I have shown you when the magnet is brought near. So when this magnet is brought near or away from the coil, then work has to be done against the force of attraction or the force of repulsion. And this burden appears in the form of electrical energy. Hence, when a magnetic pole is brought near or carried away from coil, the work is done against magnetic force. Magnetic force which appears in the form of electrical energy. Electrical energy. Hence, when the magnetic pole is brought near or carried away from the coil, the work is done against the magnetic force, which appears in the form of electrical energy. So this gives it proves that Lenz's law follow law of conservation of energy. Conservation of energy. So from this law you can find that there is a relationship between the mechanical energy and the electrical energy, and this mechanical energy is being converted into the electrical energy. So whenever there is the motion between the coil and the this magnet, then there is the induced EMF, and as a result there is the current in the circuit. So we see that here this mechanical energy is converted into the electrical energy. So mechanical energy converts into electrical energy. So this is the conversion of the energy from one form to another form. So this is about the Lenz's law. So thank you very much.